Hello, welcome everyone. My name is Sara Pulido. I hope everyone is having a wonderful DockerCon so far. I work for Datadog as a developer advocate, and on this talk I'm going to be talking about how we run Kubernetes internally at Datadog, and particularly at Datadog scale. So this talk is not about Datadog, it's about Kubernetes as we said, but just so you know, Datadog is a monitoring and analytics platform that helps companies improve observability of their infrastructure and applications, including, of course, Kubernetes and the applications that you can run on your Kubernetes cluster. As I said, I'm a developer advocate at Datadog. That is my Twitter handle and my emails. So if you have any questions or you want to follow up after this talk or later, just let me know, ping me on any of those two mediums. But this is a talk about Kubernetes. And what is Kubernetes? Kubernetes is an orchestration platform for your containerized applications. What does it mean? It's going to help you run your containers in production. And it's a completely open source project. It's a accredited CNCF project. And it's a very successful open source project. So just to give some numbers, it has had 90 major releases in 2015, more than 90,000 commits from more than 2,000 contributors. So super successful open source project. And it's not only super successful as an open source project, as well as from a user point of view. This is Google Trends for searchers on Kubernetes since 2016 until January this year, more or less. And obviously you can see that the trend is growing, steadily growing, and probably will continue to do so. But you may have noticed that there are some outliers in this trend. And when I first saw this graph, I had a theory of what was happening. And one of the things that we like doing at Datadog is putting together on the same timeline different metrics to try to find correlations. And we know that correlations is not causation, but it certainly can help you find the root cause. So because I had a theory, I decided to put on the same time frame Google Trends searches for Mariah Carey's classic All I Want for Christmas. And when I did, this happened. As you can see, it's a perfect correlation. Obviously the root cause is that it's a holiday season, people take time off work, and they tend to search less for work-related stuff. If correlation meant causation, it would mean that once a year, we don't know why, there is a bunch of people that decide to drop everything that they have to do with Kubernetes to listen to Mariah, which is another possibility. So this has been my journey with Kubernetes before I joined Datadog. So before I joined Datadog, I was working 2 years full-time in Kubernetes projects. Both from an admin point of view, so managing a cluster, but also building applications on top of the Kubernetes API. I'm a certified Kubernetes administrator, and I was also part of the team that created another similar exam, which is the Certified Kubernetes Application Developer. I'm the maintainer of YouTube Kubernetes channels as well, so where I post things that you can do with Kubernetes, concepts, etc. But then I joined Datadog, and while I was interviewing for Datadog, as part of that interview process, I had the opportunity to talk to many people on their infra team about how they were running Kubernetes, at what scale, etc. And it made me realize that it would be a great opportunity for me to join this company and to learn how people are running Kubernetes at a super big scale. And what is scale we're talking about? So just to put an example, this is one of our clusters. So each hexagon on that, it represents a node. So very big cluster, and definitely not the only one. So we run thousands of clusters with thousands of nodes on each cluster, and we run that on different clouds. And one of the things that happens when you run open source projects is that they get better as more people use it. But what if you're using it in a way that less people are using it? So I found this survey, about 800 respondents on that survey, and one of the questions was, how many nodes do you have on your clusters? And about 40% of people said between 1 and 5, which clearly means that they are still trying out the platform. 27% said between 6 and 10, which is a little bit bigger, but still. And only 4% said more than 100 nodes. Again, this is a very small survey, so take it with a pinch of salt, but it gives us an idea that there are definitely more people running Kubernetes at a smaller scale. So when you run at a bigger scale, you tend to find issues that probably you are the first one who encountered those issues. And what are those common scalability issues? So, no surprise, many of them, these are not the only ones, but many of them come from networking. As a distributed system, networking is a pain point, and people soon realize when they start that Kubernetes networking is not particularly easy. So this is where I'm going to focus on this talk. I'm going to be talking a little bit about Kubernetes networking. So I'm going to introduce 3 concepts of Kubernetes networking, very, very high level, but it will give you an idea what those are. So I'm going to be talking about pod networking, service networking, and DNS. And then I'm going to explain how people usually run those when they're running a smaller scale, and what people do, or Datadog does, when they had to move to a bigger scale. So I'm going to introduce first this concept. So what is pod networking? So a pod in Kubernetes is the small unit that you can deploy into Kubernetes. It's basically one or more containers that share the same networking namespace. So pod networking in Kubernetes basically is about giving those pods IPs and route traffic. So it has 2 basic rules that says every pod is going to get a unique IP, and every pod can route traffic to any other pod in the cluster. So that's very high level what pod networking is. What about service networking? When you have a service in Kubernetes, you don't talk directly to the pods that are part of that service, because those are ephemeral, they can come and go, you don't know where they are. So instead what you do is for example, when your front-end service wants to talk to a back-end service, that back-end service is a concept in Kubernetes called Kubernetes service that basically acts as a load balancer between all the pods that are part of that service. And that's done through a component called kubeproxy that we will see a little bit more in detail. And finally, DNS. Instead of talking directly to these IPs that for the services, you usually would talk to a name service, and that gets translated to an IP thanks to a component called core DNS in Kubernetes. So, starting with pod networking, just to summarize again, as a summary, again, every pod is going to get a unique IP, and every pod can potentially route traffic to any other pod. The trick here, this is not implemented by Kubernetes itself. You have to do it through plugins. Plugins that follow a specification called Container Network Interface. It's a spec that is part of the CNCF as well. And basically this spec tells you, if you want to write any of these plugins, what they should do and how also they can interact with each other, because actually you can mix match them. And the thing is that because it's through plugins, there are many of them and they work very differently to one another. So when people start, usually when they start a smaller scale, they use plugins that implement network overlays. An example of this is Flannel, this is a classic one, or WeaveNet. And basically what it's going to do, this is what I was doing because I was running at a smaller scale. Basically what those are going to do is they're going to create an overlay network for all the pods are going to get an IP on that network. And then they're going to have an interface, a subnet from this overlay that is going to be connected directly to that interface, CNI0, which is basically the Docker bridge. So how does it route traffic? So let's imagine that a pod in the first node wants to talk to the pod in the second node. So this is what is going to happen. It's going to say, okay, if I want to talk to a pod on my same subnet, just go directly through the Docker bridge. But if I want to talk to a pod in a different subnet, go to an interface called Flannel. And this interface called Flannel, what it's going to do, Flannel is a daemon that is going to create an IP on IP, and it's going to maintain a set of tables for each subnet, where what node is on that subnet. And then it's going to create this new packet, an extra header, an extra traffic, and it's going to pass that to the next one. So this works great, but one of the things that happens is the extra, this extra networking that needs to happen, this extra CPU of creating the IP on IP. So this doesn't scale very well. So people tend to move away from that as they scale. So there are several options. As I said, there are many plugins. One example is using the ones that run the BGP protocol to share all these routing tables. An example of this is Calico. Is super popular if you're running Kubernetes on bare metal. And basically what it's going to do is going to create a table per, so it's going to create an interface per each pod, and it's going to create those route tables that they are going to be shared between all the nodes thanks to the BGP protocol. So for example, this would be the route table for the first node where this IP is directly connected to that interface, and the second one, so the second node and the second pod on the second node, I know the next hop because those routing tables had been shared through BGP. So this is great, but it seems like if you're running in a cloud, you're duplicating what your cloud is already giving you. So you're creating a software-defined network. So what people are doing if they're running cloud is using direct port routing instead. So reusing the SDN that already the cloud provides to basically get an IP per pod coming from the VPC directly where you're running your cluster. This is where Datadog is doing, and this is what it's really recommended if you're running on a public cloud. So in this case, one of the benefits that it will have is that, well, first of all, it will match the two rules that we had. So every pod is going to have a unique IP. It's coming from the same VPC your cluster is running it. The traffic is going to be routable because you're running on that VPC. And another benefit is that not only that, you're going to have routable traffic between pods and other elements in your VPC, for example, VMs. Which is great if you're running a hybrid environment. So the first takeaway that I would say for this talk would be is that your team will need to become an expert not only in Kubernetes but also the CNI plugin that you use, because things are going to be failing. You will need to know how to debug them, etc. So the next one is service networking. And just a recap, we have a service which is acting as a load balancer between the different pods thanks to a component called kubeproxy. The good news here is that kubeproxy is actually implemented in Kubernetes itself, but it has two modes. The first mode that it can run is in IP tables mode, and this is the default mode if you're running Kubernetes for the first time. And because it's the default mode, this is what I was doing before joining Datadog. And the way it works is that kubeproxy is a component that is going to be on every node in your cluster, and it's going to watch the Kubernetes API for pods that get created and deleted, services that get created and deleted, etc. And it's going to update the IP tables on the NAT table on that node. And this is more or less how that NAT table would look like. So you have a service on the very top that has an IP that you want to talk to, And then you have a probability of 50% between the two pods, so it's random, and each of those rules will match one of those pods. This works well, it's easy to debug, but it has some issues. That table is going to grow linearly with pods and services. So obviously as you scale, it's going to take longer to find the right pod. Also for every change, the whole table needs to be resynced. And from a Kubernetes developer point of view, there is another issue. There is no room for more features. So they wanted to improve kubeproxy, and IP tables didn't accept a lot more. So here comes IPVS mode, which is a different mode to run kubeproxy. It's been GA since 1.11. This is where Datadog is running, and it has very many benefits. So it has atomic changes, so you don't have to resync every rule every time there is a change. It has different load balancing algorithms, so it's not random if you don't want to. You can use a list connection, for example, or other algorithms. And the complexity is O1, so no matter how big it is, it's always going to be fast. But also, it came, even though it was GA, when Datadog started moving to IPVS, they definitely found some issues, and therefore they had to, this is what we were talking about, of using software in a way that less people are using it, is that you tend to find issues that nobody else found before. And that's why this is, for example, an example of a PR from one of our team members who became a maintainer of IPVS, improving IPVS mode a lot. So the second takeaway I would say is that many large deployments are already moving to IPVS, and also newer solutions are being developed, like Cilium, for example, which is eBPF based. Finally, we are going to talk about DNS. Just a recap, it's just a name resolver. But it had some issues with the scale. This is one issue that people were finding a lot when scaling number of nodes, particularly in the number of nodes. This is a contract race condition that many people were having. So one of the solutions that Kubernetes came up with is to have node local DNS cache, which is basically what Datadog is doing. And in this case, what happens is that every node is going to have a DNS cache, and when a client needs to get the DNS, instead of reaching out directly to core DNS, it's going to try the cache first with a UDP connection, but then if the cache is amiss, it's going to upgrade that connection, and the connection DNS, cache, and core DNS happens through TCP, which is a first benefit. But also, it allows dropping, for example, searches that are not related to the cluster. So, for example, if the pod wants to connect to google.com, the cache will definitely drop that one in favor of the cloud DNS resolver without reducing the traffic in core DNS. Cool, so we reach out to the very end of this talk. So some takeaways. First, some bad news. Kubernetes is very flexible for developers, but it's still quite complex for your operation teams, and something to take into account. The second one would be the CNI plugins work very differently between one another, so you will need to learn how yours work. And finally, you will hit bugs as any other software, so you will need to understand how to reach out to the community, where to file bugs, etc. But there are many good things as well. The ecosystem picks up very quickly. There are a lot of companies putting a lot of effort and development into Kubernetes, so just how we saw with IPVS and DNS not local cache. This, as soon as people start finding scaling issues, there are new solutions being developed. Also, the development experience from your developer point of view doesn't change much. If you change, if you use DNS cache or not, if you change your CNI plugin, from a developer point of view, it doesn't change that much. So you don't have to make those changes in a big migration project. Also, changes don't have to happen for all workloads directly. You can create a new cluster, start moving some of the workloads, etc., trying things out. So thanks very much. I'm available for questions. So I'm going to go now to the window, to the chat window, and start answering those questions. And again, if you want to reach out, just let me know. Thank you very much, and have a nice rest of DockerCon.